Yeah, so let me begin by recalling because it's been a while. Given a representation, recall that we defined this character to be the trace of the map. Yeah, so given an element of G, you get a linear map on the vector space. So you just take the trace of that, and that is the character. So character is a function from the group to the base field. And in our study, we are assuming that the base field is C. Yeah, so we are thinking of complex representations over complex numbers. Okay, and then we saw some properties of characters. So for instance, we saw that the dimension of the representation, you can read it out from the character. So you just evaluate it at identity and you get dimension of V. We saw that chi of G inverse is chi G bar. We saw that chi is also a class function, which means precisely this thing. Yeah. And then we saw that character of sum of two representation is just the sum of the characters. Yeah, so these are some trivial observation just by looking at what is the representation of V plus W, yeah, maybe in matrix form. And then we saw that the character of the tensor product is the product of the character. Character of the dual is the conjugate. So it's complex numbers, right? So one can do it over arbitrary field, but then one has to understand what conjugate is. And then character of home VW is then you can use the fact that home VW is just V dual tensor W. Yeah, and from there you'll get so using that property and these two, you get this character of home VW. Okay. And we did some computation also. So we didn't see too many examples, but for regular representation, we saw that the character of the regular representation is pretty straightforward. So it takes the value same as the size of G because that's the dimension of the regular representation and at 1. And for others, it takes the value 0. Yeah. So you can see that the character could be very complicated kind of thing. Function, meaning complicated in the sense it's not really a homomorphism unless V is one-dimensional representation, then the character is same as the representation. Then it's a homomorphism. Otherwise, it's some weird kind of function. So it's a class function, and these two properties are satisfied, but other than that, it's sort of strange. It's a function from G to complex numbers. Yeah. So now we to prove orthogonality of the character, we define this thing. Yeah. So this pairing between characters. Yeah. So let V1 and V2 be. So actually, this definition you can do it for any two representation, not messes. So I haven't written either. So yeah, V1 and V2 be two representation of a group G, and let chi1 and chi2 be the characters. Then chi1, chi2, this pairing is between these two defined to be 1 over size of G, summation G in G, chi1 G times chi2 G bar. Yeah. So it is going to give you a complex number, this pairing. So I mean, the inputs are functions from G to C, and what you get is some complex number. So of course it is linear in the. So if you are thinking of functions from G to C, it is linear in the first variable, and it seems it's conjugate linear in the second variable, but it's actually linear in the second variable as well, if you think in the right way. Yeah. So you think of if you restrict yourself to not arbitrary functions from G to C, but to characters, it is actually conjugately is linear in the second as well. Because chi1, chi2 is, you can also write it like this. yeah, chi1g, chi2g inverse, because we know that chi2 of g inverse is same as chi2g bar. Yeah. So you can write it like this. So hence it is bilinear on set of characters of G. Yeah. So not on arbitrary functions from G to C, but on characters on the smaller collection, it is bilinear. So I'm saying because we sort of I sort of mumbled about various. I made a mistake as well initially. I mean, initially I wrote right, then I changed it, and then again I corrected it. So and I said bilinear and conjugate linear. So this is what was going on in my head. Yeah. So it is bilinear as well, but on the set of characters of G and not arbitrary functions from G to C. Though I don't think right now we won't use it, but maybe in future we may use it. Yeah. So now we want to, so what was the theorem? We wanted to prove that if we have two irreducible characters, then the inner product between two irreducible representation, then the inner product between those two characters is either 0 or 1, depending upon whether the representations are same or different. Yeah. So, if you look at this formula, this chi1 the pairing between chi1 chi2, it seems it has something to do with home v2 v1. Yeah, if v2 and v1 are representations, then what you are trying to do is you look at the character of home v2 v1, and then you sum over all elements of G and take the average. Yeah. So you take the average of the character of home v2 v1, and that is what the pairing is. Yeah. So let's observe that character of home v2 v1 is this guy. Yeah. So we will use this somehow. Yeah. So now our next goal is to understand how to get this function somewhat intrinsically. Yeah. So note that if V is a representation of G, then for any element of G, you get a linear map from V to V. Yeah, G from multiplication by the action of G on V gives you a linear map. Yeah. So of course it's not G equivariant, but if I take the sum over all of the elements of G, then of course it becomes equivariant. Yeah. And then this map from V to V becomes equivariant, because if you multiply by, let's say, G prime, then it is just summing over G prime times G with G varying on G, which is same as summing over G varying on G, and then acting. Yeah. So if you take the sum, it becomes equivariant. Sorry. Yeah. But we also want where did it go? Yeah. So but we also want this 1 over size of G somehow, and so this is equivariant. This is also, this is almost a projection map. So if you sorry, I have to do it like this. So if you scale it by 1 over G, I didn't realize I hadn't written some parts of it. So if you scale it by 1 over G, then it is this, and then also it is of course equivariant. But now let's call this map phi. Let's call this map phi, or yeah, why not? Then the claim is phi is actually is a projection map onto. So what is the image of, so let's just think about what is the image of phi. Yeah. So actually so you will see that it is the fixed, the set of the subspace where G acts trivially. Yeah, so V in V such that GV equals V for all G in G. Okay. So of course, if you take so first thing to note is that if you take an element in V sub G, then of course phi acts trivially on this, yeah, because phi V is indeed V because GV is equal to V for each of V. So for each of the, so you get size of G number of times V, but you are scaling it. So let's see a proof of this claim. So proof V in Vg implies phi V is equal to V. So projection just means that on this subspace it should be identity, and what else does it mean? And phi square should be phi. Yeah, that is how you can check it's a projection. Yeah. So phi yeah, so how do I yeah. Or another way to check is that the image of phi is so phi V is V, and another way to check is that image of phi is precisely V sub G. Yeah, that will also do it. And image of phi. So let's compute the image of phi. It is summation, so 1 over G, summation G in G, G times V, yeah, V in V. This is the image of phi, and of course this is contained in Vg, because if you apply G to this guy, if you apply so let's call it W, yeah, let's give it a name. So yeah, I use different softwares for when I've written most of it, and so it creates some problems. So so note that G dot W is just 1 over size of G. So G is linear map, so I can just so not G dot W, maybe G prime dot W is G prime G V, but this is same as W, yeah, because we are just so this is just summing over G prime G instead of G, yeah. So that tells you for all G prime in G, yeah. So that tells you that image phi is contained in Vg, and of course on Vg it is identity. So and phi restricted to Vg is identity, implies image phi is indeed Vg. Okay, so it is a projection map, yeah. phi is a projection map. So if you think about how the projection map works, so if you want to compute the trace of Fiji, so or rather, yeah. So what is the trace of phi? So trace of phi is so it is the projection onto yeah. So first let's so trace we can compute directly. Yeah. So the trace of phi is 1 over the size of g. So the claim is done. Yeah. So now I'm just trying to compute the trace of phi. So this gives us the formula of that that guy. Yeah. So it's summation g in g, trace of g, which is chi g. Yeah. So it relates to this function. Yeah. But with instead of chi1 chi2 chi1 g chi2 g inverse, it's one representation. Yeah. Which will be this guy. So trace of phi is this guy. But um, uh, so but phi is the projection onto this so phi is the projection onto this invariant on invariance of G in V. Yeah, and it is an equivariant map, right? So what will be the so what you can do is you can always write V. So we know that you can so V sub G is a sub representation of V, and you can always get a complementary guy. Yeah. So V is equal to V sub G direct some W, where W is some sub representation of V. Yeah. So you can always write it like this. And what does phi does? It is the projection onto this. So now if you think of taking a basis of V sub G and then extending it to a basis of whole of V, then try to compute or maybe you can just directly do characters. So what is yeah. So what is what will be the trace of phi if you think in these terms? So it is so phi. If what does phi do? It's identity on V sub G and 0 on the W part. Yeah. So W is in fact the so this is how we got it, right? So W was in fact the kernel. So phi is equivariant. So W is in fact the kernel of phi. Yeah. So in fact it is kernel, and this is the decomposition you get. Okay. Because phi is equivariant. So the kernel is also a sub representation, and this is how you get. So trace of phi is basically yeah. So yeah. So what do I want to say? Yeah. So maybe I don't want to say. Yeah. So maybe I want to relate chi of V with these two. Okay. So chi of V is chi of Vg plus chi of W. But what is chi of Vg? So VG is a trivial representation. Yeah, so everything acts via the trivial guy, right? So chi of VG is just yeah, so chi of VG of any element is just the dimension of VG. Yeah, so so if you think of VG as so VG is a sub-representation, look at its character. Then since it's a trivial representation, this is not only for identity but every G, it will be dimension of VG. Yeah? For all G and G. Okay. So, so this trace of this so note that phi is identity on VG. So what am I trying to say? Yeah. So so somehow I want to relate trace of phi with this guy. Yeah. Yeah. So phi is the identity map on VG. Yeah. So this is also trace of phi is also so trace of phi is also dimension of VG. Yeah. Since phi is projection onto VG. Yeah. So on so what it means is on VG it's identity and on W it is 0. So if you start with a basis of so trace does not depend upon the choice of basis. Yeah. So if you start with a basis of VG and extend it to and a basis of W and then write down the matrix corresponding to that, then it's identity and zeros everywhere. Yeah. Does that make sense, guys? So if you compute the trace, you'll just get as many number of copies of ones as the dimension of VG. Is this clear?
Yes, sir.
Yeah. Okay. So we get this. Yeah. So now yeah. So somehow I've used more space than I wanted to. So yeah. So. I don't know how to make, so in the other one, there was a good way to make space. Here, I don't know how to do this. Move it down. Yeah. Yeah. Okay. Yeah. So now, or maybe I could have. Yeah. So let's ignore this space. Let's get to the theorem. Yeah. Okay. So now let's prove this. This proposition is what we wanted. Yeah. So if V1 and V2 are irreducible, then chi1 and the inner product between chi1 and chi2, this pairing between chi1 and chi2 is 1 and 0 other. So 1 if V1 is equal to V2. So V1 and V2 are isomorphic, and 0 otherwise. So now let me give you the so this is just some linear algebra. Now let me give you a proof of it. So one will be this using this conceptual thing, and then I'll get to the shares proof. Yeah. So proof of this. So note that home V1, V2. So if home V1, V2 is a representation, yeah, is also a G representation. Also G representation, and but it need not be trivial representation. Now, if you consider home V1, V2 things, so those linear maps between V1 and V2 which are fixed by G, then what does this contain? This contains, so this is the set of linear maps. So maybe I'll need more space here. So so is the set of linear set of G equivariant linear maps from V1 to V2. Yeah, because I mean, this is what it means. So you remember what the formula for the action of G on, so how we thought of home V1, V2 as G as a representation, yeah, right? So what was the formula? So so the formula was G phi so the idea was G phi G inverse W. So it's difficult to remember that way. So I'll just write it down this way. Yeah? V1, V2 is phi, and V1 is G, and G phi is this guy, and V2 is here. Yeah. So then it is easy to write down. So G1, G phi of GV1, GV is same as first you apply phi to V, and then apply G to it. So, and then G dot. So this the second one is action. So G dot phi V is the action on V2. Yeah. So this is how it was defined. Yeah. So if you are trying to figure out maps which are fixed by G, that means G phi. So we want to know when G phi. So we are looking for maps which are for which G phi is phi. Yeah. So G phi is phi if and only if for all. Sorry. So G phi is phi for all G in G, if and only if G phi of G, sorry, not yeah, GV. This is okay. G and G phi. So G phi is phi. Yeah. So is equal to, so I can replace, I should replace G phi by just phi. Yeah, if and only if. So phi GV is equal to G dot phi V for all G in G. Yeah. So phi lies in this fixed thing, if and only if this happens, which is equivalent to saying that phi is G equivariant. Yeah, that is the definition of G equivariant. Right. So this set consists of equivariant maps. Yeah. So now you just apply what we did. So now if V1 and V2 are irreducible representations, then they are same, then the number of so then we know so okay, so space. So if V1 and V2 are G, so if V1 and V2 are irreducible representation, and then, so now we'll use Schu's lemma. So by Schu's lemma, if V1 equals V2, then home V1, V2 fixed. So number of G equivariant maps between V1 and V2 is one dimensional. Is one dimensional. Yeah, because it's given by scalar multiplication. Every linear map from V1 to V2 is given by scale. So once you identify V1 with, so even if they're isomorphic, then this is going to be one dimensional. Yeah. So you take one map, and every map is just a scalar map, multiple of that. Yeah. So that tells you that dimension of home V1, V2, G is 1. But so this, but now you use this formula. So dimension of V sub G is trace of this projection map, which is same as 1 over G chi of summation chi of G. Yeah. So this is same as 1 over G summation . So I'm just trying to show so the formula we get is dimension of V sub G is 1 over. So this is the formula we'll use. Yeah. So I should have written this more clearly. Summation chi G, G in G. So maybe I'll write this more clearly here. Is dimension V sub G. Yeah, so this is the identity we'll use. So this is dimension chi home V1, V2 of G. Yeah. So I'm just using this this formula, right? Dimension of V sub G is this guy. So just that our representation V is now home V1, V2. Yeah, instead of just some arbitrary. And that is 1. So we get that this is G in G. Yeah. But this is same as 1 over size of G. So maybe I should have done V2, V1. So it doesn't matter whether I do V1, V2 or V2, V1. So the formula will come out properly if I do V2, V1. So let's just do that. Yeah. V2, V1, V2, V1, V2, V1. Yeah. So this, of course, now we can use the character for the home. So this is chi, chi1, chi2 bar G, chi1 G, chi2 bar G, which is precisely chi1. Yeah. Okay, so that takes care of when V is equal to V2. And if V is not equal to V2, then of course we know that this equivariant thing is there are no equivariant maps. Yeah, so you get C. So let's just write that line as well. So finally, if V1 is not isomorphic to V2, then home V1, V2. So this of course is not zero. This is same. I mean, this is a big space, but we know that if both V1 and V2 are irreducible, and then there are no equivariant maps between V1 and V2. It's zero by Sue's lemma again. Sue's lemma. Because the set is same as set of equivariant maps between V1 and V2. Hence, this chi1, chi2, this pairing, which is by this formula, if you trace it, is same as dimension home V2, V1, G is 0. Okay. So that completes the proof of this this proposition, which was orthogonality of the two characters. Yeah. Any questions? Okay. So if there are no questions, let me proceed. So I'll give you another proof, which is the Sayre's proof, which is somewhat more computational, but it uses the corollary which we proved last time. Yeah. So I'll recall this corollary. You guys still with me? Yeah. Okay. So recall this corollary. So if V1 and V2 are two irreducible representation and H is any linear map between V1 and V2, then you can make these conjugates. Yeah. So you can cook up using these conjugates. You can cook up this map H0, which will turn out to be an equivariant map. Yeah. Because of this conjugation thing. And then as a consequence of Sue's lemma, you get that if V1 and V2 are not isomorphic, then H0 has to be the zero map. And if V1 and V2 are indeed isomorphic, so that means V1 and V2 are both the same representation. And then H0 happens to be 1 over n times the trace of H. Yeah, so times the identity map, if you like. Yeah, so it's just multiplication by trace of H over n. That is what H0 is. And this is irrespective of which H you choose. Yeah. So H you started with some arbitrary linear map. If you do this, then if V1 and V2 are are not isomorphic, no matter which H you choose, this method will always lead to 0. Yeah, H not to be 0, or otherwise 1 over n times trace of H. So we will. So there is there are matrix interpretations of these two statements, and that is what Sayre uses to prove this orthogonality So he deduces some consequence of matrix interpret. So we will just see what the matrix interpretation is, and that leads to Sayre's proof. Yeah. So so rho V1G will so if you fix a basis of V1, then it will be given by a matrix, yeah, AG. So which I mean, it will depend upon the element G of G. Yeah, so given by a matrix AG for G in G. So given any G in G, you will get some matrix which will depend upon G. Yeah. And similarly, rho V2G will be given by some other matrix BG. So the size of the matrix AG will be same as the dimension of the vector space V1. Yeah. So I'm not writing the size, so because maybe not don't want to introduce too many variables. Yeah. Too many symbols. Similarly, so rho V2 will be given by some matrix B, rho V2G will be given by BG. And then the matrix, so H is some linear map from V1 to V2. So that also will be given by a matrix. And that need not always be a square matrix. So it will depend upon the dimension of V1 and dimension of V2. But let's call that matrix Cij. Yeah. So I'm just, so this formula I'm going to write this maybe I should now I can. So this formula I'll write it in terms of matrix multiplication. Yeah, and then these two statements will be will be a statement about certain functions. Yeah. So C is the matrix of H, which isCij's. So the entries areCij's, and C0 is the matrix of H0. Okay, with respect to the fixed basis of V1 and fixed basis of V2. Everything you fix a basis of V1 and V2, and you get these matrices. Okay. Then this H0 is definition of H0 tells us that C0 A, B, and C has the following relation. So C0 is 1 over G times BG inverse C AG. Yeah, it's rho V2 G in G inverse, but that is same. So remember, rho is at least a homomorphism, so you can put this inverse inside. Yeah, so write it as rho V2 G inverse. Okay, so see, we get this this matrix identity. Yeah. So the first statement says that if V1 and V2 are not isomorphic and they are irreducible, then C0 is 0. Yeah. So if you translate this, in terms of this matrix formula, so I have removed 1 over G, but maybe we can carry it on, or let's not worry about it. Huh? So 1 over, I mean, if 1 over size of G times this is 0, then of course this is also 0. So this guy right hand side is 0, but if you expand right hand side, then it is, so this multiplication is over so for each I comma lth entry of this matrix on the left hand side is basically Bij G inverse Cjk AKL G. So this is how the matrix happens, and you sum over J and K. Yeah. So it is just matrix multiplication, and then you sum over all G in G, and you get that this must be 0 for all I and L. Yeah, because C0 is the 0 matrix. So this is 0 is the matrix 0 matrix, 0 matrix, and this is scalar now. So since H is now note that H was arbitrary, right? So this identity holds for no matter which H you put, yes, or in particular which C you put. Yeah. So this is 0 if V1 and V2 are irreducible and not isomorphic. No matter which C you put, this identity will hold. Yeah. So this holds for arbitrary Cjk. Yeah. So if it holds for arbitrary CJK, that means if you collect the coefficients of CJK in this left-hand sum, then that coefficient must be zero. Yeah, otherwise, you can, if that coefficient is non-zero, then for some CJK it will not be zero. And what is the coefficient of that guy of a particular CJK? It's this, yeah, Bij G inverse AKL summation AKLG summation over G in G. Yeah, so we just change the order of this sum. Yeah, put G inside, and then for each JK, this expression must be zero. Yeah, that is the coefficient of CJK. Yeah, so so we get this identity. But this, if you think in terms of functions from G to in the group G to complex numbers, and look at it as this inner product. So then this is AKL BIG. Yeah, so AKL is a function from G to C. Yeah, it's a matrix entry of A, but it's also a function from G to C. So this is just that pairing. Yeah, so maybe we'll have to go back here. Yeah. Yeah, so it's this guy. It's this guy. Yeah. So this we can also, maybe I should write this here. So this we can also think of it as this pairing. So this is the notation which is used in share. Yeah. Maybe some variant of this. Yeah. So this is for all complex value. So this is for all complex valued functions on G. You can define this pairing, and by this formula. Okay. So here A and B need not be characters for some function. Yeah. So I'm just using some notation instead of writing this in this form. I'm just using this notation so that it becomes somewhat handy later on. Yeah. So what we get is that since this was this is zero, that tells us that this is zero. No matter which IJKL we choose, we get that this is zero. Yeah. So that is the interpretation of 1. Similarly, we can try to interpret 2. So what does 2 say? So if 2 says that if V1 and V2 are same and their representations are same, so the representations are same, tells us that B must be equal to A. Then this C0 is just 1 over n times the trace of C times identity matrix. That is what C0 is. It's just the multiplication by this scalar trace of C over n. Yeah, so let's just try to understand what this formula in terms of matrix means. So of course C0, we know what the formula is. So we computed that here. Yeah. So the left hand side of this guy. So I've just copied this with Bij replaced by Aij. Yeah. So Aij G inverse CJK AKL G, and then you sum over JK and sum over G in G and 1 over G. So that's the left hand side, that is familiar. Now the right hand side, we want trace of C times identity and in the diagonal entries, and off diagonal entries we want 0. Yeah. So let's concentrate on the diagonal entries. So we want a trace of C times 1 over n. So trace of C, we can also write it as Cj sum over all Cjk, but we don't want to take all Cjk. We only want to take those Cjk where J is equal to K. Yeah. So one way of doing that is write delta Jk. Yeah. So delta Jk is the Kronecker delta function. So maybe I should have written that here. So delta Jk is 0, J equal J not equal to K, 1, J equal to K. Yeah. So that is so this expression inside computes the value 1 over n times trace c, and then of course this should be the value of the entry if I and L are same. Yeah, otherwise it should be 0. So another way of writing, so left hand side is the ILth entry of C0, and right hand side also is the ILth entry of that product. And the right hand side, I want it to be the ILth entry of C0 in this terms. So 1 over n trace Ci. So it is this. Yeah. So I hope this formula makes sense. Yeah. So I hope this formula is clear to you. Yeah? So it's just so left hand side we already know, and the right hand side is just this matrix. Okay. So now if you now again you you equate the coefficients of Cjk. So on the left hand side, so if you equate the coefficients of Cjk, so if you fix Cjk, then what you get is that so for fixed jk, you'll get 1 over size of g summation g in g aij g inverse akl g, and on the right hand side you have 1 over n delta. So remember, c again, c is arbitrary. So so this holds for all Cjk, means the coefficient of Cjk on either side should be same. Yeah, so is 1 over n, and the coefficient of Cjk on this side is 1 over n djk dil. Yeah, which is basically 1 over n when j is equal to k and I is equal to l. Yeah, otherwise 0. And left hand side again you can interpret it in terms of that inner product. So it's akl comma aij inner product. Yeah, because g inverse is with aij and g with akl. Okay, so these are the interpretation of 1 and 2. Yeah. So once you have this interpretation, then of course you just try to prove this. Yeah. So prove that orthogonality. So now if V is an irreducible representation with character chi, then what is the this pairing chi over chi? That is just 1 over g chi of g times chi of g inverse. Now that is the formula, which is same as 1 over g. Chi of g is the trace, right? So trace of this is so if the representation of v, so we are in the setup when v1 and v2 are same, and the representations are both given by the matrix A. Yeah. So then this trace is just AIIG, and trace of G inverse is AJJ G inverse, sum over I and sum over J. Yeah. So this should be sum over I, this should be sum over J. So I've combined it and written it as sum over I and J. Yeah. So we get this, and now of course you take the sum outside and put this sum over G inside. Then and then of course this and then you push this 1 over G inside as well. Then what you get is this is just pairing of so now you use this notation. Yeah, this one here. So this is just pairing of AII with AJJ, and you have to sum over all IJ. Yeah. So of course so yeah, so now we can just use this result. So this is 1 over n only when j equals k and I equals l. So you want j equals k and I equals l. So that will happen only if both I and j are both same. Yeah. So this is the sum over I and j, but I and j should both be same, otherwise it's going to give you 0. And when I and j are same, then you get 1 over n, where n was the dimension of the representation. Yeah. So this is dimension of the representation. So I will so here the sum is also again same as the dimension of the representation. So you get this one. Okay. So that proves the part one part that the character of irreducible representation, if you pair it with itself, you get 1. And then the part 2, you instead of this identity, you'll use the previous identity. Yeah? So if V1 is different from V2 and irreducible representation, then if you do this pairing, then you use the same formula, but now chi G inverse is replaced by chi1G, chi2G inverse. And then you get this BIIG, AIIG, BJJG inverse, and again sum over G. So this formula becomes sum over Ij, AII, BJJ. Okay. And this if V1 and V2 are irreducible, then this pairing was always 0. Yeah, no matter what these indices were, K, L, I, J, no matter what they are always 0. This pairing is always 0. So that tells you this each of these term is 0, so the sum is 0. Okay. So that again proves the orthogonality relations. So since I messed up the proof, I gave you 2 proofs, and hopefully, so one is in Sayre and the other is sketched out in Fulton and Harris. Okay. So I hope this orthogonality relations are clear now. Yeah, and using the orthogonality relations, we also last time saw that we could decompose a representation in uniquely as they are sum of irreducible representation with some exact coefficient. Yeah, so any representation B, we could write it as V1 power R1 up to Vn power Rn, where V1 to Vn are some irreducible representation, R1 to Rn are some numbers. And you can also get these numbers. Yeah, so the way to get these numbers is you just pair the character of V1 with character of V, and you'll get those numbers, R1, R2, and so on. Okay. So that was the proof done in the last class. So any questions? So maybe we can stop the class now. So stop recording.